Welcome back to EET 260 microcontroller applications. We're going to talk about keypad matrix scanning. This technique is used all the time. There's a ton of gizmos out there that have keypads on them. Even if they don't have all the digits or all the letters of the alphabet or whatever, anything with more than a few buttons is often scanned. That is, the keys are often connected in some kind of matrix and scanned. If you just have, say 4 different buttons, well, those could go directly to the input to a microcontroller. But in this case, with 16 buttons, that would use up 16 pins. And let's say you had a 5x5 matrix, that would use up 25 pins. Whereas if you scan them, you only use up 10 pins. In our case, we would use up 16, but we're only going to use 8. So that's a good, that's a good trade-off. And it's just a software technique that allows us to do this. The way now this keypad that I'm using in my experiments is every bit the same as the red and blue parallax keypad that you will be using in lab. I think that's what you'll be using. The whole idea is that these switches are normally open single pull, single throw switches, and they're momentary. So they close momentarily while you have your finger down on the button. The other thing to remember, these little buttons actually are pretty good at not bouncing very much, but every button bounces. That is, it'll start to make contact and it'll wipe and the crud can get in there, and so you might make contact, break, make again, break, and make again. And we'll show a technique to provide for debouncing the switches here in software. Now, the way these switches are arranged, and I'll show you a schematic in a second, but where this particular wire right here says row 0, I'm numbering the top row across here as row 0. And I'm numbering this as row 1, row 2, and row 3. And this black wire here goes to a pin which finds its way, you might even see the trace in the board here, finds its way up to row 1, and it connects across here to, row 0. It connects across here to all 4 switches in row 0, and that would be S1, S2, S3, S4. And this other black wire goes to a pin, and I don't think you can see directly, but it goes to column 0. So if I were to press switch S1, I would produce a short between this row 0 wire and the column 0 wire. And here, let me, I can shrink this down just a little bit. There we go, now you can see the whole thing. So if I were to press S6, then I would be shorting the row 1 wire to the column 1 wire. If I pressed S12, I'd be shorting the row 0, 1, 2 wire to the column 0, 1, 2, 3 wire. So it would be column 3, row 2 would be S12. And so you can get the general idea of what's going to happen there. So given that, take a look at my setup. Here's my switch, and to see enough of this, I had to kind of move out, so you might not see all the details, but trust me, the microcontroller is hooked up just as I said, and right now P0 through P7 are hooked up according to this document. P4 through P7 will be outputs, and P0 through P3 will be inputs. And you can see the columns are pulled up by 10K resistors, 10K ohm resistors to 5 volts or VDD here. And so if I don't have any buttons pressed down and I look at these inputs, they will all be high. They'll all be a logic 1. If any of them is pulled to a 0, then it's because I've driven a 0 out on one of these lines and a switch was pushed. So if I drive a 0 out on P4 and any of these buttons are closed, S1, S2, S3, S4, then on the appropriate column line, it won't be high anymore. This low on P4, when the switch closes, will pull that down. And if it's the very first switch, S1, P0 and P4, P4 will pull P0 down to a 0, and I'll see 0, 1, 1, 1. So I can tell if a button's been pushed because one of the inputs will be low. And this is more typical of the way this is done in the real world. Some people will do these examples where they, drive the resistors go to ground and they drive them high, and it's just not really done that way. In fact, most microprocessors include these pull-up resistors into the inputs, maybe a value in the 27 to 47 k ohm range, and that way you don't even have to populate the board with these 4 resistors. You can configure the inputs to either have or not have these pull-up resistors, and that's great for things like this. Now I don't have my basic stamp in here and my power supply is turned off. I'm going to use my meter on the the continuity test section here, and I don't know if you can hear that, but it's indicating continuity there. So I have the red wire plugged into P0, and if I plug the black wire into P4, there's P4, and I press the button for column 0 and row 0, that will be this up here, this will be S1. Hopefully you can hear that. There's a little beep there. That's being shorted. Now I can press any other button on the entire thing and I don't get that continuity. The only button that will give me continuity between column 0 and row 4 is this button, which is labeled S1 on the board here. Hopefully you can hear that. I don't exactly know where my speaker is on here, or microphone is on my laptop, but that's the amazing power of my continuity tester. Now if I were to go, let's take another one. Let's say we went to P2. So that was P0, 1, 2, and we went to P7. Now P2 and P7 would be, let's see, P2 is this one, so we'd be in this column 0, 1, 2, column 2, and P7 would be the bottom row. So it should be this guy right here. Column 0, 1, 2, row 0, 1, 2, 3. So column 2, row 3. There, we got the beep. Okay. All right. So having done that, I'm going to put my microcontroller back in here, violating every rule known to man, and turn it on, and I'll probably have to reestablish the USB UART driver here, and I do. And so I'm going to connect that to the Windows side of the machine, and we're going to look at some code for scanning this keypad. And the code that we're going to use is what we call state machine code. So let's take a look at that code. We'll go over here to the Windows side. And we'll bring up our code. And what I'll explain is that at the top of our program, I have a couple of byte variables. These are variables that can hold from 0 to 255 as a value. One is called KP state, and people call this a state variable. It holds, if you were just counting a sequence of events, like a player piano, or let's say a music box. A little music box might play, 64 notes. So you could have a counter that runs from 0 to 63. That's 64 different values, and that could be a state variable. So in state 0, you would play a certain set of notes, and in state 1, you would play another set of notes, and in state 2, another set of notes, all the way up to state 63, and then maybe repeat the sequence. So a state variable is a way of keeping track of the sequence of some process that you want to achieve. So, and KP next goes along with KP state. Every time you consider whether you want to change state, you will put the next state into the KP next value, and then after you've done all your testing and everything and you're ready to go for the next cycle, if you will, you would copy KP next back into KP state and go look at what you're doing. And you'll see this in the code. I've also defined a bunch of constants. I have 5 states that I'm considering here. Idle means no keys are pressed. KP det 1 means we've detected a key press once. KP det 2 means we've detected that same key press twice. And I'm running this either every 10th of a second or every 20th of a second. We'll see that down below. But the idea is to debounce a keyboard or a switch. You usually want to see if it's been held in the same state for a couple of times. One might even want to do this 3 times. I've done that in the past, but usually twice is good enough. And KP det 3, it's used because once a key is pressed and once we detect it and find that the key is has been detected, we don't want to do anything until the key's released. I shouldn't say that. We want to launch some activity, but we don't want to launch any other activities until the key is pressed. So if you had a start button, you might detect the depressing of the start button, but and start the sequence, but you wouldn't really look for other buttons while someone's holding the start button. All right. So that's just a typical way that people interpret keyboard presses. There is a keyboard algorithm called rollover, where a second key may be pressed while a first key is down, but even then they really don't release the second key until the first key has gone away. KP signal is just a state. I'm kind of wasting a state there, if you will. It's just a state during which I can set a flag to 1 to let the program know that we do have a key press, and the key has been pressed. We're handing it to them, and we won't give them any other keys until that key's been released and a new key has been pressed. And these are some variables here: KPD new, row new. These, in fact, KPD new I don't believe is used in our program anymore. Maybe I'll take the risk of getting rid of a couple of these variables to clean things up. Watch. Well, you know what I'll do? I'll just comment them out. There's a programming technique that's used quite a bit. So I have row new and column new. Those will be the row and column, or column and row, if you will, where the key was detected. And row old and column old, I do this so that I can remember what was pressed, so that we can see it twice before we decide to accept it. That's our way of debouncing the key, is saying you have to show it to me twice. So again, there's a couple of variables here that we don't that I had originally in here and we don't need anymore. I'll comment those out. So where we have row new, column new as variables, row old and column old as variables, and we initialize all this stuff. We make our KP state equals, well, instead of 0, well, let's give it the more readable name is idle. And I think just to make, even though we don't need to do this, it's good practice to set next state equal to idle too. Just really initialize this stuff. We have one more variable, KPD. That's the variable we use to signal our program that a key has been pressed, and that's initialized as 0 as well. So the first thing we do as part of the initialization is we make sure that P4, 5, and 6, and 7, the outputs which we would drive low one at a time, we make sure they're all high. Our main program is pretty simple. It says we're going to repeatedly, you see the do in the loop, we're going to go execute a subroutine called read 4x4 KP. If KP equals 1, then we're going to print out column and the column number. We're going to print out row and the row number, then a carriage return, and we're going to wait 50 milliseconds. So we're going to do this every 20th of a second. Now, what is go sub? If you haven't done this before, a technique used in a lot of programming is when you have a routine that you want to execute, from a number of places in your code, or you want to execute it repeatedly, you can make that code into what's called a function or a subroutine. And in this case, in BASIC really doesn't have functions. This kind of BASIC anyway. Visual BASIC does, but this kind of BASIC doesn't really have functions. It just has subroutines. In which case, you remember where you were when you executed the go sub statement, and so you say go subroutine read 4x4 KP, and we have a label down here, read 4x4 KP. And we jump down here and we execute all this stuff that we're going to talk about. And in the end, you do return. And return says, go back to that place you remembered. In other words, basically go back where you came from. It comes back here, and then it executes the if statement, and then the pause 50. Of course, it'll loop, do the go sub again, go down there, do what it does, return, execute the if statement, pause, and so on and so forth. So let's see our go sub here. When we come down, we initialize the. Let me get rid of that. Should have been disconnected before. Hopefully, I didn't do anything bad there. But one of the things that we're going to do here is we're going to initialize that variable column new to 128. And you'll see why. What we're going to do is we're going to lower, we're going to drive a 0 out on pin 4, P4. And if input 0 is low, well then the column that we detected must be a 0. Else, if input 1, P1 is low, then the new column must be column 1, because we saw something low there. Else, if input 2 is low, then column 2 must be active and we've detected something. Else, if input 3 is low, then column, here, let's do this. Then column 3 must be the column where we've detected something. And if not, well, and here's the deal. If we change the value of column new, see column new started out at 128. If we change the value of column new, so if column new is no longer equal to 128, then row new equals 0. That's because we detected this driving P4 low, which means we have row new is 0 and column new is whatever it was up here, and then we go to finish, and you can see the finish one labeled down right down here. So we make that input 4 high again, and now we'll try input 5. We'll drive input 5 low, and we'll do the same thing. We'll check and see if input 0 is low, or input 1 is low, or input 2 is low, or input 3 is low, and we'll set column new equal to 0, 1, 2, or 3 appropriately. And if we changed its value, so if it's no longer 128, we will set row new to 1, because pin 5, driving pin 5 low attests column row 1. And if if we did detect something here, we go to finish, so we don't try anything else. Likewise, if that's not true, if we were not able to find anything there, we set 5 high, because we only want one of this P4, P5, P6, and P7. Only one should ever go low at a time. So we put 5 back high, we make 6 low, we do the same test capturing a column new value. If column new is not equal to 128, then we must have caught something. So our new row new is now 2, and we go to finish 1. And and if not, then we'll make P6 high again and try the same thing with P7. And if not, then P7 is high. And now, if we fall down here, we look at our state, and we say, this select case type statement says take a look at the KP state variable. That's our state variable, right? KP state. If it's idle, make sure that KPD, that variable, is a 0. And if the column new is not 128, we must have detected something. So KP next will be equal to KP det 1. That's the state where we've detected a key press. And row old equals row new, so we remember the row number that we found it on. And col old equals col new, so we remember the column number we found it on. If col new is still equal to 128, then we didn't find anything, and KP next will be idle. We'll just stay in the idle state. Now KP detect 1, if we are in KP detect 1, we still keep the KPD signal low. If col new is not equal to 128, that means we must have detected something for the second time. So if col new is not 128 and col new equals the col old, in other words, if we detected something on the same column and we detected something on the same row, then KP next will be KP det 2, meaning we've detected this thing twice. Otherwise, we just go back to idle. It means that we've got some noise or something, and we're gonna have to go back and start at idle. All right, so let's look at KP det 2. So if we had come down here in the KP det 2 state, we still set KPD to 0, but our next state will be KP signal. All right, so we do that. Now, by the way, when we drop through this case select statement, we update our KP state with KP next. We make sure all 4 of our outputs are high, and then we return. And we do that whole thing over again. And so every time we visit here, we are testing the keypad array and computing what state we should be in. So if we're in KP signal, then we make KPD 1, and that's going to tell the main program that we have a keypad, key press that we like, and we're going to report up to it. We set KP next equal to KP detect 3, and we fall through. We set all these guys high like we do every time. And of course we set KP state equal to KP next. So the next time we fall down through here, KP state will be KP detect 3, and we make sure that KPD is set back to 0. We also look and say if the column number is not 128, that means we're still detecting some key press. So no matter what, just set KP next equal to KP det 3. In other words, stay in this state as long as something is pressed. Otherwise, if nothing is pressed, then your next state will be idle. You update your KP state, make sure all the outputs are high, and you return. So that's our scanning routine. It scans for, using a state variable, KP state, it scans for a key press. It scans next time for the same key pressed. Then it goes to a state where it signals the main program that it has a key press that it likes. Then it'll come back and continue to wait until there are no keys pressed before it goes back to the idle state. And we can kind of draw that, the logic of that state machine here. Let's go back over here for a second. And we can say, here is the idle state. And if we have a key press, so we can say if we have some kind of a key press here, okay, then we can document this as much as we want, but I was going to kind of keep it simple here. Then we go to the KP det 1 state, and if we have the same key press again, we go to the KP det 2 state. But if we have not the same key press, if we have no key press, or different key press, we go back to idle and begin again. All right. So now we're in KPD2. The next thing we do is we go to KP signal, and in all of these things we make KPD equal to 0. So KPD, the variable, is equal to 0. Here's KPD equals 0, but in this state we do KPD equals 1. Okay? Then And there's no conditions here. From KPD2, we will go to KP signal. We'll issue that KPD1 equals KPD equals 1. Then we'll go to KP det 3, and I guess the way we can draw this is we'll say here is any key pressed, or here we'll say any key pressed, or just say any key press, and here we'll say no key press. So if there's no key press, we go back to idle, and of course from power up or init, we go to idle. But if there's any key press, we just stay in KP det 3. Oh, and of course KPD equals 0. Alright, so that's our state diagram. We call this a state machine. This kind of thing is a state machine, and you can build these in hardware in digital logic, or you can build them in software with programming and variables. State machine diagram. And sometimes when you have to make some kind of sequence of something with conditions, a diagram like this can be helpful. But you do have to be careful, because there's a lot. You have to take care of every condition here, and if you don't, you could be missing something in your state machine. So it's helpful. It's just a way of taking a look at this kind of stuff. Now, so I will scan this thing and put it into the document, and so you can have it as part of the keyboard scanning document. State machine diagram for keypad matrix scanning code. So that's a software state machine. All right, let's go back over now and see how our thing works. Again, I commented out some things, so I'll take those out of there before I post this code. And so we'll download this thing. And I should talk about what it does here in the main program. The main program calls our subroutine go sub read 4x4 KP. If that KPD variable is a 1, then it prints out col and the column number, the old column number, and row and the old row number, prints out a carriage return, and then waits a 20th of a second and goes again. So I'll go column 0 row 1 over here. The camera's not part of this side of the machine, but so I'm on column 0 row 1. I'm holding the key down, and now I release it. So it only showed up one time. It said column, so we're debouncing it fine. I will try column 3 row 1. Column 3 row 1, column 3 row 2. How about column 2 row 3? And I can hold it down. Here's column 1 row 3. I can hold it for as long as I want, and I just get it one time. So you can see our state machine is working. It's processing key presses, making sure that they are experienced or seen on the inputs 2 times in a row. If they're seen only once and then something else is seen, or the key press has gone away, it goes back to idle and starts over again. But once it sees the key press twice in a row, the same key press, it will eventually issue the KPD equals 1 variable. The main code will see it and print this out. Now, the main code, instead of printing this out, could go off and do things. It could be, you could have statements there, and based on the key codes, a lot of programs will have key codes in some kind of table for dispatching the actions that it wants, and maybe column 0, row 2 might be to launch a missile. So there you go, column 0, row 2, missile is launched, and then column 3, row 3 is recalled a missile, and fortunately we saw column 3, row 3, and we blew the missile up. So that's really it as far as my take on keypad scanning. It happens all the time. It's done in lots of gizmos. If you're working with those kind of those variable speed drives like the GE or I'm trying to think, Allen Bradley or whose ever drives you're using. Some of them now have a little detachable keypad that has a microprocessor in it and enough intelligence to kind of authenticate, so only people with that keypad can walk up and reprogram the variable speed drive or something like that. Well, it's kind of neat the way they do it. It's got a display and a keypad in it, and you scan that keypad and look for key presses and pass them into the brains in the middle of the drive that arranges for whatever speeds and feeds you want that thing to do. So you go to the gas station and go to fill your car and have to put your ATM PIN number in there. Well, there's a keypad that's being scanned for that, and at the point of sale terminal, same kind of thing for your PIN number, but also the same thing for the person on the cash register. They have a big keypad matrix there, and they scan it. And the same thing happens in your PC for your QWERTY keyboard there, 104 key PC keyboard. Those keys are all arranged in some kind of matrix or array, and they are scanned. There are rows and columns, and they are scanned, and a key press is processed carefully so you don't get bounce, and it's then passed into the computer for processing there. So I guess that pretty much covers it. And so our next discussion will be about binary and decimal values. And so I hope to see you soon. Take it easy, and I hope all's well. Bye-bye.